Hello, this is to section 5 of the Firenock Dealer certification class. And see, we're finally dealing with arrows right now. All right, let's start. What makes an arrow, how the arrow move, and what makes a good and bad arrow? That's what we're going to talk about. You see, after every component go onto the arrow, what are we really trying to accomplish is that the arrow is the way you call the frame of everything that goes onto it. Your knocks, your vanes, your points, your inserts, your inner tube, they all go into the arrow. Now we build stuff that go in everybody's arrow. But let's talk about what good and bad and what matters. And this is going to be quite complicated because, you know, as we move into a faster and faster arrow projectiles, a lot more things that we don't think is important begin to show up. Okay? First of all, let's talk about spine and deflection. Because this is what matters the most, the spine and the deflection of a shaft. By the way, they are not the same, okay? The spine is about how the backbone of the arrow is. The deflection is how much it flexes. So in other words, just like a shaft, how much it flexes in what way it flexes. How much it flexes is deflection. The how it flexes is the spine. Now you can see that, assuming this is the tail of the arrow, this is where the string going to push. This is where the weight of the field point and the insert, where the momentum is. So this is what the arrow going to flex under, quote unquote, the static energy of the field point and the insert with this. The more it flexes more, you get deflection more, which is called lower spine. But does the arrow just simply flex up and down like this? No, it do a lot more than that. As a matter of fact, we know that you actually have torque strength. That means when the arrow flexes, you don't just flex this way, you also flex this way. Because remember, the end of the arrow is on the knock. This is where the field point and broadhead is. The moment this don't move, when it flexes, it may cause it to twist. That's the torque strength. That's how it resists the twist. And then we also the torsion strength. That means that the front and back is twisting on the opposite side. And sometimes it can be more, which is like a lot more than this and this simultaneously. Then, is that all it is? No, that's actually even more to strength. This part, a lot of people recognize loop springs. The most they recognize it is where the end of the arrow is. Because that's where the knot goes in the outside. Of course, the outside knot is different than an inside knot. So when you try to push the knot around, in other words, the loop of the arrows would hold the knot in. But also in the middle part, when you bend the arrow, if you do a cross section of the arrow, this part of the arrow is actually will turn oval. That's where loop string come into play. Because without loop string, you really don't have much spines at all. So in other words, the arrow actually going to go like this as you shoot it, as it flexes. Now let's go back again and rethought. So when the arrow flies, when you compress it, 4 things happened. You flex up and down, you twist front and backward. In the meantime, the entire OD of the shaft will change shape. This is what we know an arrow do when you shoot it. So, what did we do in the history of time to overcome this? We know that first of all, the arrow has to be reasonably straight. And the natural material used, like bamboo. Then we go into split bamboo, cutting bamboo outside edge to glue them together. Because we try to get rid of the notches right here. Making less and less effective. It's the same method the British used to do their split bamboo fly rod. Then, of course, notice a lot of people like cedar, poplar, ash. What they're using is the outer edge most of the wood. They have the least amount of knot in it. Because you're trying to get a consistent fiber through it. But of course, modern material kick into play, like aluminum. Aluminum is really good, especially most of the aluminum arrow is made of 70-75. But so how come we didn't stick with aluminum? Because of metal fatigue. We all know that when you hold an aluminum tube with bending a few times, eventually you lose its strength. That's called metal fatigue. Then Well, a lot of people say fiberglass is great. Yeah, but fiberglass is also very heavy. And of course, finally, we use what we use most now, carbon. Carbon seems to have addressed all the major issues. But as we know, carbon is not simple carbon. In today, what do we use carbon on? Fishing rod, lacrosse, golf club, arrow, and also some of the ski poles, and even boats. But let's talk a little bit about this whole deal. You notice that every single tube right here are the same except one. Every one of them is tapered. It is very, very, I mean, this is the only time we notice that there's a major difference in arrow. Every one of this is tapered. Yes, we do notice some people build arrow with a minute taper in it. Like this end, some people may have 3,000 different from this. But this is so little, it's not important. But this is still the only parallel tube around all of this. Why is this such an important thing? Because until you understand the fundamental difference and why a taper and parallel impact, you can't go the next step. Because in like this one, you hold here, you hold here, you hold here, you hold here. In other words, every one of them, the moment you have matched the reaction of this arrow or the golf club, which is called spine matching, the moment they're tapered, the spine usually is linear. In other words, as long as you've got a tapered shaft, you can very easily build a linear spine after you find the spine. But when the tube is parallel and you use carbon, this don't happen. Well, let's go into it, say how it did not happen. Let's go into ask the question of what first dynamic bend is, because without understanding these terms, what I just tell you don't make much sense. The moment you're tapered, you can select, in other words, your first dynamic band actually behave like a diameter all the way through the center of the tubing, because it's continuous from large to small. Okay? So this is what ideal is. This is what you can do achieved when you've got a tapered shaft. But what is an arrow? The arrow is not tapered, it's parallel. So that when this thing bends or flexes, even if you change direction, assuming this is an arrow, it flexes and it turns, you can see every one of this flex curve is an ellipse. That means when the arrow flexes, if you've got a linear spine and it's going through the center, that means flex between these 2 points. The first dynamic bend is the first one, and the second dynamic is within the same axis going through the center as a diameter. You end up with the flex curve of the shaft in the form of an ellipse. Very uniform ellipse, and that's ideal. But what is actually happening in most of the carbon arrow today? Of course, this actually happens in aluminum a lot. That's the reason a lot of people in critical part go back to aluminum, because they can get an ideal homogeneous environment with the flex curve on the first and second going through the center. But what actually happened in carbon fiber, especially most of the carbon arrow out there, this is what you really get. The first dynamic band and the second dynamic band are no longer passing through the center, but you can see that it's a curve. And the curve is nowhere even linear. In other words, this is not a logarithm curve, this is you do not know it. That's the worst part. There is no fixed formation of any of curve. Every single arrow approach will have some form, and they are not this. That's the bad part. Every carbon arrow you made do not have this. You know how come I know about this? I'll tell you how I know about this when I describe PAPS, which is a later stage. So in other words, think about it. If this is your first dynamic band, this is your second, or in some arrow, this is your second. What is the arrow? The arrow is no longer elliptical, isn't it? That means when the arrow spins and flexes, it's no longer elliptical format. It's more like a triangle. Because think about it, when this thing's on, this whole thing will be oblong and down, up and down, and up and down. In other words, it is no longer a very elliptical orbit. The orbit is ridiculous. And you don't know it, what it look like. The only thing you know between these two diagrams, what's the only thing you know? The starting point. What does this starting point stand for? First dynamic bend point is the only thing we can count on. Okay, I want to describe this in a little bit deeper so you understand what that means. Imagine this is looking through the arrow, cross section. You're going to feel it. Now, first of all, this is not a defect. This is quote unquote a curve of describing how you feel around the shaft when the shaft behaves. So in other words, this is not a dimple, but this is what the effect of the arrow when the force curve pressured. This is the first dynamic bend for most of the carbon shaft, or any carbon shaft they have, when you apply pressure in the middle of it, and you'll feel this valley. And in most cases, on most carbon arrow, you'll feel the second valley, usually around 7 o'clock or 8 o'clock, but usually feel 2 only. So in other words, for this specific shaft, when you feel that through the force curve, the arrow going to flex through this called arc or curve right here. But this is not the norm. This is what we want in carbon shaft. But not ideal, but this is what we get for most of the high quality carbon arrow. But what happened to low quality carbon arrow? This is what you actually got. So when you find an arrow that had more than 2 so-called first and second dynamic bend, you got first, second, third, fourth, fifth, sixth, you can't shoot this arrow right no matter what it is. This is a bad arrow. That's reason in some cases when you find an arrow and you find out in the old days, a lot of people try to find the arrow on the first dynamic bend looking for imperfections. Oh, this thing is, you will put on the gauge meter, you can find this or found this. But what you are finding, you can find this because of what? You can find this because the material is the same, all the way around it. But now, this is totally different, because when you do multi-layer carbon, you feel multiple dimples, and that becomes very difficult. But so how can we easily find this or this, even in this situation? Because as long as I find the dominant, it's at least reasonable to be used. But ideally, you want to have that. So how do we find it? Well, in the old days, people would like to use, we'll put this whole arrow inside the tub and float it. The heaviest will on the bottom, because it's a homogeneous material. When the heaviest on the bottom, guess what? The lightest on top. The material is the same. But what happens with a carbon arrow? Does carbon fiber resin weight and ratio have anything to do with strength? Nothing. What's carbon composite with fiberglass? Does resin, carbon fiber, it may have some relationship, but remember, you're wrapping multiple layers of that. It really don't mean anything anymore. Remember the first picture we talked about when we compress the shaft like this way and the arrow eventually flags just like we do? Well, that's theoretically a great approach, but we cannot possibly compress the arrow perfectly, perpendicularly every time. So the two edges on it, so some people say I put on bow press or somebody will put it on a vise. You damage the shaft first before you find the first dynamic bend. So how do we overcome all this? Well, that's what I have done back in 2009. I invented PAPS. Because I found out, actually this was because of AeroBolt. I figured that using an aero concept system, I can minimize the effect of spine. The truth proved me wrong. I mean, yes, the carbon aero concept arrow will make a spine less important, but spine is actually more important than anything else we know of. So the only thing left is that we know we can't overcome it, so we might as well use it. Because what happened that when you know exactly how the arrow flexes, the first dynamic band becomes the only thing you can rely on. So, how do you find the FDP, first dynamic band? That's what I designed. At first, I wanted to design a super sophisticated machine. You will read the reading for you and you can find it. The fact is that I cannot possibly do that. The sensitivity of the machine would be point of ridiculous. And you would be so expensive that nobody can afford it. So what I did, I used something that we are all born with, super sensitive, the tip of your index finger. Your tip of your dominant hand's index finger will give you the most amount of indication without paying so much because we're all born with it. And in order to lower the initial friction, I added this. That's a vibration module. You notice my fingers up there? What does that actually do? First of all, I center the roller on roller and ensure the arrow is at the end of the rollers. What does that really mean? That means I want to make sure that I center the shaft, because at the end of the day, when the arrow bends, it bends right in about the middle. So I center 2 of the rollers and with this thing in the middle. And this is what I would do. See that? And you notice on the APS and the PAPS, I always leave this side with the ball bearing right here. You know why I did that? So that I can be reasonably close to the end, but without being to the end. Because if I just do it on the edge right here, the roller can roll off. I don't have the consistency in it. So I always suggest that make the carbon at the end of the APS roller block. So now you have even distribution of the entire shaft in length and find the center. I'll roll the arrow in the finger. Now, a lot of times people say, just roll back and forward. No, 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 you don't do that. You roll it one direction using one finger. One finger, very important. If you put more than one finger, you will confuse yourself because you have too many contact points. One finger, you go backwards with one direction until you feel the valley. Then you push it forward. The moment you find it, you push down the finger to confirm it. So you're using both hands to confirm that. The moment you found it, you need to mark it. You mark it always on the very top side. That's how you mark the first dynamic band. Now, if you're not sure, roll the arrow again. You'll find out you're going back to the same spot because the only contact point is 1, 2, and the bottom of this. So what you're really making contact is 1, 2, 3, 4, 5, 6 points on the entire shaft. Remember, this is not a square, but a crown. Now, the moment you find out all this, okay, there is ways to help you. Because see, this is not a simple tool. In some way it is, but it is not that simple because we have a lot of things in case. Since I built this baseboard, this base plank, you can see the 2 APS support roller is here. This right here is called the center tower. This, of course, is the digital module, and this go with it. By the way, this is different from the other guys. What the other guys? This whole thing is called a digital module. And this thing is not 1.92 pounds because this is only part of this equation. So this piece plus the brass underneath plus the 3 beam plus the lower piece with 2 ball bearings and the load of the spring combined will give you 1.92 pounds. But at the same time, if you really was going to look for what is the spine value of this shaft, make sure you stop them both at 14 inch because it's 28 inch apart, 1.92 pound total weight, 0. Now this is a 0. That's your 0 indicator, your 0. And now when you put this thing back, put the arrow down, then you 0 it. Because without beginning point, you don't have end points. That's how you get the true value of it. Oh, because when you read the number, it don't mean anything. Remember, we have the lowest point. So what you do is that, first of all, you mark the arrow, which is your 0. You bounce it once, you get the reading, your first number. You rotate the arrow 180 degrees, you bounce it, you got a second reading. Then you rotate 90 degrees, you bounce it, you got a third reading. Then you rotate again 180 degrees and bounce it, you got a 4 reading. With that 4 reading combined divided by 4 is the actual spine rating of this shaft. That's a spine rating. That means how much this arrow will averagely deflect when it's under load. A lot of companies use this tool. This is actually a great tool. I don't use it much because see, what's the point of knowing the spine number of your shaft? You bought it. That's the reason this is only needed if you are cowling your shaft, or if you want to know how good you make the arrow shaft. When you bought it, okay, you got 5, 10, 12 arrows, and 3 of them is, say, you want 300 and 3 of them is 270. What are you going to do? Throw them away? Yes, that's pretty much the only thing you can do. Now this part, a lot of people got confused, but I think this is one of the more useful too. Because remember, this is still a mechanical piece. And now there's friction everywhere. There's friction on the bearing, there's friction on the truss, on the linear bearing, there's friction on the lower bearing, there's friction everywhere. So how do we lower the F0, the initial friction? By putting energy in the entire system. That's what the vibration module is for. It is nothing more than a heavy brass unit with a tiny computer with a motor in it, which give out a lot of vibration, which lower the entire F0. Why do you want to lower the F0? So you can feel the individual valley and top of the entire shaft. So, what's next? The laser module. This is actually not needed. You might as well forget it. Of course, if it's nice to have if you already bought an AeroWing jig, because this is for refletching. Then you can, I will give you, this is what you buy extra. This top piece is 25 bucks. So now you can mount it just like this with the light shining on like here. Why do you need a light shining on it? Because see, when you mark the top part, unless you're exactly up on top of the shaft, how do you know the marking on the very top or the slightly edge? You do not know. And when you start doing hundreds of shafts, it gets very tiring. With the laser, it's going to be the top the first time, every time. So you can just mark it. That's how what the laser helps you to mark. It's help you to mark the markings. There's nothing more than that. So what's next? Well, a lot of you guys say, oh, you know, I can just get something else, and then maybe I will make some. I'll use the APS rollers for the PAPS. Well, let me tell you that that's a very bad idea. The reason that is a bad idea, let me show you exactly why. You see the APS and PAPS from this way, you look identical, isn't it? But they're not. This one, because of the feet, you notice how wide the feet is compared to this? This you want absolute linear stability, and you also got an index in it. Which means that I can go cheap with this. I will just extrude this, cut it, and machine it, and be done with it. If this thing rocks this way, have no big major effect. But this is a measuring instrument. Now, in other words, this is a reference instrument. It has to be very solid on the base. And when I say 28 inches, this mark right here will tell you exactly. By the way, this is not a line. It's actually a V. So at the end of this inside is an absolute. And this go to the edge of that crown. So when you have this line pointing at your APS or PAPS number saying 14 inches on one side, it's exactly 14 inch. Now I've got the PAPS right here, I will show you. So when you move this right here and you say 14, see that? You can now precisely, see this line and 14 go exact because you got a reference line here. While the APS, you have no such thing. So everything become a guess. Remember, this is a reference instrument. That means everything you build, if this is not right, the rest is not right. So, now you learn about the spine, you learn about the torsion, and you know we make all the components. Let's talk about what everybody is thinking. First of all, before I say anything, I want to say everything we learn about aero is correct as long as you don't shoot over 260 feet per second. This is going to be really hard for a lot of people to understand, but as I go on, you will see what I mean. First, number one, strictness of an arrow shaft. We all know the more strict it is, the better it is, right? The answer to that is yes. But this is only one of the many components of an arrow. You start with 1,000 strictness, you should be able to build with a better arrow. When you talk about 1,000 strictness, or more precisely that, 1,000 strictness, what are we talking about? This is what the measurement is. Support an arrow at 28 inch with a laser mark in the middle. Rotate this thing, whole thing once. If the center portion of it on the laser guidance, say 0.001, this arrow is 1000 straighteners. But what does that mean after you have the first dynamic band, after you have the components? So whatever you put an insert, that gives you 3000s on the end. So what does the 1000 do with that 3000? You just lost it. What happened when you put 1000 straighteners and put 3 vanes on it? They're out by 5 degrees. This is only one number of the entire process. But the fact remains, we already know the arrow was never ever straight in flight. The arrow is doing 50 to 100,000 in flax during its flight. So I can confidently say 1,000 to 8,000, as long as built correctly, with the right component and also with the first dynamic band aligned, they are the same. Yes, I claim 8,000 to 1,000. If the arrow is built correctly, it will fly the same. Will the 1,000 be better? Slightly. This is more important to get the vanes, the insert to be done right. So, what does that mean? I literally just busted the 1,000 is the most important factor. No, it is not. As a matter of fact, the first dynamic band is. So how about shaft size? 166 all the way to, say, the usual 300,000s. What is the best size arrow? People claim that the thinner the arrow, the better the penetration, the larger the arrow, the least the penetration. Answer to that, what do you use it for? What are the difference between this arrow besides the OD? Now remember, no matter how thin or thick the arrow is, the spine number do not change. When you buy a 300 spine 166 and 300 spine 300, they both have the same identical backbone, which is spine deflection. Okay, so what did the 160 have to do to behave like a 300? The wall thickness had to be a lot thicker, which means that this arrow have a lot more slower reaction compared to 300. And of course, somewhere between is the ideal. We at Firenock believe the 202 and the 246 is the ideal. Because most of the product are designed with 8mm in mind. The 300 be a little bit bigger size, but think about it. The 300 is still a very good size. If you think about the old day of a 2219, 2216, the 300 is the same size. It's about 300,000 OD, which gives you about 325,000 OD. The 166, in most cases on the thick wall, everything's done, you're still dealing with about 260,000 on the OD. But a 202 with a thin wall, you end up with the same. So the only thing you're getting is that you are getting a smaller components and more complex components. So again, is thinner better? No. On top of that, when you have thick wall, what does that mean? That means the arrow, when it flexes, it takes a lot more effort. And when it recovers, it takes longer, which means the duration of the flex is longer, which means the arrow lost more energy on the high let-off bow. Yes, high let-off. The higher the let-off, the thicker the wall, the worse it gets. Which does that mean? Oh, we say, well, you know, I shoot fantastic, 260 feet per second. Yes, you are shooting slower speed. The moment you shoot slow speed, everything you learn is true. But the moment you shoot high speed, no. Everything changes. So where do you begin to change? About 260 feet per second. When you're going to see a major difference is 315 feet per second. 350 feet per second and above, that's where everything we talk about, straightness, diameter, you can pretty much throw them out the window. So, again, thinner is not better. Finally, FOC, oh my God, this is a can in the worm. The can of worms. Everybody believes that the higher FOC, the better the arrow, the control, and so on. It's like telling people, the slower you drive, the better you drive. Yeah, we know that. Absolutely, the slower you drive, the less chance you make an accident. But what does that mean? You have no performance. Everybody knows you drive a highway at 45, 55 miles per hour, you should never have an accident. But who drives like that? If that's the case, why would we even bother to buy a 335 feet per second bow? Or shoot a 400 feet per second arrows on crossbow? But then, the fact is that the moment you start shooting high speed, front of center becomes very difficult because it is every single error you have in the aero build exaggerates. So what happens is that you keep on loading the front, so you have directional control. But in the meantime, if you lower the front, load the front with heavy weight on a thin aero, you only tell there's a huge amount of directional momentum in the front. What happens if the front don't move, the midsection don't move, and the tail will swing like a dead fish? Now you got vanes on it. You got a parachute. Yes, the air will fly very nicely. You'll fly very slowly, and everything is easy. But what you really try to accomplish, if that's the case, you might as well go back 10 years ago, buy a 260 feet per second boat. You get the same result. So why would people still go with front and center? Because they can't get it to shoot right. Because they don't know how to tune the bow right, and they for sure don't know how to tune the arrow or build the arrow right. So if you build the arrow right, from what my experience is, if you build an arrow with the right components, and everything is right and shoot high speed, with 80% of that off, you can be around 8 to 10%. Most people believe 12 is good. 12 is not a bad number. 12 is a very, very generalized number. But the moment you go high speed, you went with high let off, you really, really, really want to drop the front of center. Because right now, the moment you do a high let off, with high front of center, you defeat the purpose of using high let off. You actually, yes, if you don't shoot over 25 yards, you can pretty much do anything you want. But the moment you shoot high let off, high FOC, you lose so much energy. Give you a hint. You can lose as much as 40% energy at 60 yards, using 80% off at 15% FOC. That's how much we're talking about. If you are 65% off, you can only lose 12. No, lose 28, sorry, from 40 to 28. See, and let's sort of push the envelope a little bit. What happens if I put a whole aero concept system, lower the FOC down to 8%, and shoot everything right, tune everything right? How much are we losing? Actually, Mr. Wright, the Rod Wright, the gentleman with Olympic, have do a test for me. He found out that if I do everything right, tune everything correctly, at close to 8% FOC at 60 yards, I lose between 8 to 12%. Not 40, not 38, not even 25. That's how big a deal that is. Was that easy to accomplish? No. But the thinking process, high FOC means good, is wrong. Okay, now we talk about all this. So how do we accomplish what we want to accomplish? But first we need to look at how we build arrows first. Long time ago, when the first carbon arrow, now think about it. When you look at the fiber coming this way, what does it make you think of? Bamboo, cedar, fiberglass, and carbon. It's called a unidirectional carbon. In other words, all carbon go in the same direction, you just roll it all. What's the downside? Well, the downside is that you have no loop strength. That means the moment you break it, you spur out. Have no torque and torsion, because remember, all fire straight, there's no way to prevent on twisting. And that is, you only have one way to build it. You roll the whole thing in a mandrel and call it a day, or extrude it. That's what the original carbon fiber is. Now you know why we use outsert, because you have no way to protect this two end. Now you know why the old Beemans, they all have outserts and outknocks, because you prevent this from bursting, because there's no loop strength. So what do we do next? Well, I remember when Gold Tip comes out and a few other carbon, they all use this approach, which means that every carbon fiber go into an angle and you lay multiple layers, 15 to 30 degrees, one over the other. Now what do you get out of this? You get significant better loop strength. That's absolute, because now the fibers are overlapped. Okay? But what's the downside of this? Again, you still have that unidirectional process in it. It's still layer of carbon. The control of the entire torsion is unknown. And in most cases, this layer of formation, remember, when one layer over the other, if they are exact the same thickness, every one of the layer is larger than the other. Because that's the nature of the game. You lay the next layer higher, bigger loop, bigger loop. So what happens, which is more dominant? Answer is you have no idea. So what does that mean? When you do this, You end up with better loop strength, torsion strength, and torque strength, but you also have one major problem. This arrow is guaranteed to give you a helix spine. That means the spine is no longer linear, like the original aluminum. Or like this one, have multiple spine on the back, because at least you know which way it bends. This one you have no idea. The spine can be like this, or like this, and then go backwards. That means it can be a single helix or compound helix spine. That means the torsion effect of this arrow is high. It's yes, you can do calculation, correct it to minimize it. Some companies do a fantastic job in it, don't get me wrong. Some are very, very well engineered. But this is, we're talking inherited design flaws, okay? So what other ways do you do? Combine all this. Get more spine length to make it lower weight using this part of one of the layers, and using 90-degree layer to give you fantastic loop strength. So you got loop control, you got spine strength, and you give you a little bit of loop strength. All three. So this is pretty much the current arrow direction. So you can see that the approach is all try to address what I just showed you. So what did we do at Firenock? Well, we start with AeroArrows. Now, we saw all the things that we already discussed. Now let's go and address them from a scientific point of view, from an engineering point of view of every single factor. How do we overcome all these problems and maintain what is needed? We start with the quote-unquote a true 1-to-1 ratio weave. When you have this, when you twist it, you're changing this into a diamond when you twist it and torque it, right? You got this length for linear, and you got this supposed to be spine strength, but in effect, this have no spine strength at all, because the fibers are looped like this. And if you look at the diagram, this, by the way, is from outside in. The second layer under the first layer is actually this form, which is same fiber but rotate 45 degrees. Now what does that mean? That means if this thing have to flex, you're changing the amplitude of the diamond. But when you lay these two together, what does that mean? That means you can't do any of those, because this will counter the effect of this. But this itself have no linear strength. That means if when you put together, you need so much material to get a spine number to be up. So these two material is not enough. We want an arrow to a spine. Spine as deflection resistant. That's the reason we added this layer, which is the same thing, high modular, linear, directional. This is this is like everybody, because this is the layer that gives the arrow its spine number. The first two layer and the fourth layer are the same, which I'm going to show the fourth layer. This is the only layer that gives you the spine rating of a shaft. So if you want an arrow from 400 to 350, you increase this. From 350 to 300, you increase it even further. But this is not a good inside layer. You need a base layer. And that's what we did. We use the same material on the first layer, we use on fourth layer. So imagine this, when you roll all this together, what do you get? You get absolutely spine capability. This will give you spine deflection resistance. Another way, give you this. This will prevent it from doing this. And if you can do this, this two layer will constrain it. So all of a sudden, you got this. Now everything combined, this is no rocket science. This simple mechanical engineering. If you control the force from every single direction, the whatever left is what you can do, is this layer. That's the reason now all of a sudden, you got a carbon arrow with a linear spine, with torsion control, torque control, and loop strength. A lot of people say, well, everybody use weave nowadays. Yes, I understand that. But let's take a closer look at what weave is. This is the weave we use. It's a 1-to-1 ratio. This is what most people use. Herringbone is a 1-to-2 ratio. This, unfortunately, this fiber in the 4K fiber is very heavy. That's the reason people like this. Because we're talking this compared to this. This is much thinner. This is much lighter, much easier to use, and it's cheaper. This is a much more complicated. Because imagine if you're weaving this take about a half the time more than this. Because this is a 2-to-1, this is a 1-to-1 ratio. We already know that 4K weave in this form, the only major downside is weight. So how do we overcome it? You can see that we make everything out of the weave. But you notice there's something different. See right here? And not to mention this is an 0204. But the new 204 have the same one. And this is what you're looking at. This is the 4K weave we will currently use on our 315, 300, the 246, and the 0204. But when you move into the 166, the new 204, you're looking at 1K weave. Why is 1K weave such a big deal? Because we significantly thin the fibers a lot more. When you thin the fiber a lot more, that means you have more layers. That means the resin between the fiber is less. Which means now I can have the strength I need without sacrificing weight. All of a sudden, you got the best of every world, except one small problem. Carbon fiber cloth in this class are sold by the yard, not by weight. So if this thing weighed 1/5 of that, and I use 2/3 more, I just up my price by about 50% on raw material. Which explains why the 166 and the 204 is $219.95 a dozen, while the rest is $159.95. Actually, it should be a lot more. But since we control every part of the factor, the fact is that raw material cost is only a portion of the entire cost. That's the reason we're able to maintain it. Is it cheap? No. $219.95 for a dozen of raw shaft? In actuality, with no distribution center, no wholesaler direct to dealers, you will not know how good you have the material. Yes, is it cheap? No, it is not, but it's worth the money. So, with all this stuff we talk about, you do know that AeroWeave is what's going to be our main part, which is going to AeroBolt 3. The AeroBolt 3 that we make is exactly based on AeroBolt 2. One difference, this is actually an old arrow from one of our suppliers. We do not make this. We just have a label on it, okay? But from now on, the AeroBolt 3 is based on our AeroWeave. AeroWeave 300, 200 is what AeroBolt 3 is. You can see identical everything, we have everything now. So what's the difference between these two arrows? Well, this arrow is 8.9 grain per inch. This is 10.5 grain per inch. So it's a lot more heavier. But we prove again and again, the moment we control the rotation, the bend for the first dynamic bend, and every component, if even this arrow is heavier by say 40 grains, yes, initial 20, 30, 40 yards, it will not hit as high as this, but this will hit higher the moment it increases, because it has so much better in conserving energy and expends the energy in flight. That means it conserves a lot more energy compared to this, even it's heavier. So this will actually hit higher at being heavier. This is hard to explain, it's hard to understand. So at this moment, I just want you to take my word for it, and you can try it. Because the moment you have this aha moment, you understand why Aero Concept and the AeroWeave arrows are so much better. Because until you try that, it's really hard to imagine. Well, you remember this is the dealer class, and I'm going to emphasize this, the SPORTWEAVE. The SPORTWEAVE is a line of arrow we made for dealers and dealer only, which means that only certified and trained dealers are allowed to sell this. What does that mean? It means that Firenock as a company, we will not sell this. The only people who are allowed to sell this are certified and trained dealers. Yes, that's how serious we are about our dealer network and training the dealer we have. So we are giving you this entire series of arrow called SPORTWEAVE, and only you can sell it. What is so special about this? This arrow, technically using everything we learned and everything they have done, using the machine that we have made for the best. And because they are not using the heavy weave we have, without the complex pattern we have, we're looking at $89.95 a dozen. So you got technically the traditional arrow on the first 2 layers or 3 layers, and wrap that with a 4K 1-to-1 ratio weave. That's what it is. It is a very economical arrow with everything we know on the manufacturing process, not with the pattern. And this is what we offer you. The 246 and the 300. On the crossbow on 2 sizes, there's a heavy and there's a light version of ours. You notice even our light version is still 10.3, our heavy is about 11.6. While on a 246, we go with the general. Because we want to give you a very durable, reliable, consistent arrow at a budget price that you can build as your launching pad for your arrows. So, we're talking everything front to back. You talk about 1, 2, 3, 4, now we're in the 5th sections. What are they? First section, we talk about Firenock. Then we talk about section 2, we talk about vanes, right? Remember, they are all ours. Then we go into outsert, arrow system, arrow bushing, arrow insert A, field points, arrow points. We have our broadheads. We have mechanical piece now. And all the arrow insert H, hybrid system with arrow concept. See, the tube can go to the back of it. And the new 166 points. Remember, we're here to help our customers. If they want to shoot the 166, give them the best. Because until you have this, the 166 is hard to deal with. Outsert is okay, but this is a whole different level. Especially with target guys. Remember, this one got arrow concept in it. And then for the target guys, we have the Destroyer series, the arrow concept point for the Pro ASA IBO shooter, and finally, the entire line of arrow tubings or shafts. And yes, I did not put CIT in it because there's no room. But you can see right here, this is where the CTI will fill in right here. You can see, take a closer look. Everything we made, and we make more. Like this one. This too. We don't even make 235. This is 235 stuff. Okay? And in these cases, we don't make anything over 315. And we make all those. The bottom line is that I give you an entire list of components that can fit every single arrow in the market with the best components. Remember, at the end of the day, I sell those. But selling them is not the only intention. It's to teach people like you, my dealer, to learn how to use this stuff to build the ultimate best arrow for your customers. Because I don't know them, you know them. You can use mix and match any of these components and build them the best arrow, no matter who built the arrow shaft. Now remember, Firenock do not build arrow shaft until 2 years ago. So everything you see here is to fit every single arrow. So if your customer love, say a Black Eagle, or Eastern, or Goated, be it, you still have the best component know-how. You can still put arrow concept in it, you can still put target system, you can still put arrow wing in it. But this is where you come in as a dealer. Now, with all this thing right here, how do you know which one to fit? This is where I build you an ultimate tool. Look at this. This is called Firenock Arrow Component System. Search engine, Finder. Actually, the moment you go to our website on the upper right-hand corner and you click on it. Component selector. I want to show you how to use it. So you know, with all this whole lot of component, how do you find it? You go ahead and click this. It'll bring you to our arrow component selector. I have loaded every single arrow that is currently in the market that I know of. So you can see I have every manufacturer here. So we simply say we go to Black Eagle. And then the moment you click Black Eagle, it will show you every single arrow they made. Say we go, say Executioner, or the better, Deep Impact 600. The moment we do that, look at this. It shows you the picture of the Deep Impact 600 and every component that will fit it. All the way down to the broadhead and arrow and also Firenocks. And then you can now pick and choose what you need. So in other words, with this tool that we wrote on our website, with the knowledge that you have for the entire last 5 sections, you should be able to build the perfect arrow for your customer after you learn this. All right? So if you have any questions, let me know. And the next sections all about bows. This is the end of the arrow. That means we do end-to-end the arrow and component and everything. This is the end. And if you have any question, email me, iMessage me, whatever. I'll try my best. But if you understand everything I talk about and use this tool correctly, you pretty much got it all wrapped up. All right? Thank you.